In this video, we'll go over the answer key for Friday, April 24th. And what we're looking at today is our Michaelis-Menten equation. So Michaelis-Menten kinetics is a way for us to measure the speed of an enzyme, and it's also a way we can measure how tight our enzyme binds to our substrate. And the reason we have this is so we can compare enzymes that do different reactions to each other on an equal footing. Now, the equation we use for enzymes that follow Michaelis-Menten kinetics is shown here. Enzyme plus substrate will make our enzyme-substrate intermediate. It does it with some speed K1, which is a rate constant. Now, this enzyme-substrate complex can also break down to enzyme plus substrate, and it does so with some speed or rate constant of K minus 1. This enzyme-substrate complex can also make product plus, freeing the enzyme again for another reaction. This has a speed or a rate constant of K2. And that gets us to our overall equation. Now, we derived the equation in the video, but we just need to know how to use the equation for right now. And our equation is our initial velocity of our reaction equals the Vmax, the maximum speed of our enzyme, multiplied by the concentration of substrate we have in our enzyme, divided by this constant called Km, the Michaelis constant, plus the amount of substrate we have in our reaction. Now, this Km value is different for each enzyme and substrate complex. What it tells you is how much substrate do you need to get to go 1/2 your maximum speed. And we can actually show that mathematically. So let's say that the amount of substrate in our reaction is equal to Km. And as shown in this table, Km is just it's a number given in molarity. So if we have the same amount of substrate as Km, then what we would have effectively is Vmax divided by 2. Because let's say, for argument's sake, Km was 2. So we have 2 plus 2 because our substrate is equal to our Km. So that's 4. Well, substrate's also at the top, so we have a 2 here. 2 divided by 4 is 1/2, or Vmax divided by 2. So when our substrate is equal to our Km, we are going half our maximum speed. Now, what does Km actually mean? Well, if your Km is a small number, a low number, that means your enzyme can reach its maximum catalytic speed at low substrate concentrations. It usually means it binds your substrate well. It will want to go and find the substrate, bind it, and move to the transition state. Now we have another term to talk about is kcat, or the turnover number, or how many reactions can you do per time. And that is your Vmax divided by the concentration of enzyme you put in your reaction, or enzyme total. And when we have Km and kcat together, we can divide the two. Kcat divided by Km is called catalytic efficiency. That is an overall number we can use to determine how efficient all of the enzymes you ever study are. Your most efficient enzymes have kcat divided by Km of 10 to the 8 or 10 to the 9 inverse molar inverse second. We call these diffusion controlled limited. That is, the slowest part of their reaction is the time it takes for a substrate to diffuse over to them. Once they run into a substrate, their reaction is more or less instantaneous. The slowest step is actually movement. Now, we're going to learn how to look at Km using a table and a graph. So first, our table. Here we have substrate concentration, and here we have Vmax. And so you can see the substrate concentration is growing, but our V initial, I think I called this Vmax, but this is our V initial, our speed at the beginning of the experiment. It tops out at around 1200. Going from 50 to 500 to 5000 really didn't have that much of an effect on our speed. So let's say our maximum velocity is 1200. We can't go higher than that. That means half our Vmax would be 600 millimolar per second. Now we have to use this table and estimate what substrate concentration would give us an initial velocity of 600. And that's roughly somewhere between 3 and 5, closer to the 3 range. So I'm going to say it's roughly 3.5 millimolar. That is the Km of this enzyme. And we can also use a graph to do it. So here is our initial velocity versus substrate concentration. You can see it's rising. Now we haven't plateaued yet, so our Vmax isn't 4. We can say our Vmax is roughly 5, because if we keep adding substrate, we can expect it to level out, but keep going up as well. So we can make an estimation at this point. Say the Vmax is roughly 5. So if Vmax is 5, 1/2 Vmax is 2.5. And to find the concentration, we have to draw a line until we hit our curve. And then when we hit our curve, we have to drop another line down. And so our Km for this is at 1 millimolar, we are going at half our maximum speed. Therefore, Km is 1 millimolar. So question 3, now we're getting away from the graphs and tables and we're using these equations. So I have an enzyme that has a maximum velocity of 2.68 molar per second. I run an experiment and my initial velocity is 1.25 molar per second. My substrate concentration is 0.22 molar and my enzyme total is 0.34 molar. What's Km, Kcat, and catalytic efficiency? So let's do Km first. So we use our Michaelis-Menten equation. Vmax velocity initial equals Vmax substrate divided by Km plus substrate. Well, Vmax is 2.68. The amount of substrate we have is 0.22. And so my initial velocity is 1.25. So I plug in all my variables and I'm left with Km. So I need to solve for Km. The first thing I do is multiply my denominator on each side of the equation. And I get 1.25 km plus 0.275 equals 0.5896. This 0.5896 is coming from multiplying my Vmax and my S together. I then subtract 0.275 and then divide each side by 1.25. My Km is 0.252 molar. Right. So now I need to figure out Kcat, so that's a separate equation. Kcat equals Vmax divided by enzyme total. My Vmax is 2.68. My enzyme total is 0.34, so I divide the two, I get 7.88. Now I can do catalytic efficiency. So Kcat is 7.88, Km is 0.252, which means my catalytic efficiency is 31.3 inverse molar inverse seconds. Now we can also find out Km and Vmax through a Lineweaver-Burk plot, or what's called a double reciprocal plot. And these were used before computers could do advanced fitting. So we can figure out the Michaelis-Menten equation by doing a nonlinear fit, or we can make our measurements form a straight line if our axes are 1 over velocity and 1 over substrate. And when we do that, we'll see where we cross the y-axis. If we take the reciprocal of that number, it's Vmax. Or where this point crosses the line is 1 divided by Vmax. And where we cross the x-axis is 1 divided by Km. So let's take a look at this. We actually have a Lineweaver-Burk plot. So what's Km and what's Vmax? So Vmax is where we cross this intercept. So that's roughly 1.8. So 1 divided by V equals 1.8. So you do 1 divided by this number to get Vmax. Vmax is 0.56. Now our other number, 1 divided by s, if we do that, 1 divided by s is roughly negative 2.7. So I do 1 divided by that number, negative 1 divided by that number, and we get Vmax is 0.37. So that's how we use a Lineweaver-Burk or a double reciprocal plot to figure out what Vmax and Km is. Sorry, this is supposed to be Km. I'm not sure why I put Vmax twice, but that is Km. Now let's look at the different types of mechanisms we can have in our enzymes. First is what's called we're going to look at bisubstrate reactions rather. And we have two different ways we can do a bisubstrate reaction. We can be ordered or we can be random. And both of these are sequential. And what sequential means is that all of our substrate has to bind before our enzyme can do its reaction. So we have two substrates, A and B. They have to bind before we can make the products P and Q. So ordered means A always has to bind and then B has to bind. We always release P first and we always release Q last. That's what's called ordered. Random is it doesn't matter which one comes on and which one comes off. A could be on first or B could be on first. The enzyme can happen either way. But they're both sequential in that they have to combine with the enzyme before a reaction can occur. Now, that is different than a double displacement or ping-pong mechanism. In a double displacement, one reaction or one substrate binds and a product is released. And our enzyme has changed. So E and F is the same molecule, but they're slightly changed. So once we're in the enzyme conformation of F, you can think of that like hemoglobin R and S state almost. But once we're in F, our second substrate combine, that release our second product. And now we're back to start. And the way to determine if you have a sequential where both substrates have to bind in ping pong is you can do various experiments and figure out the two. We're not going to get into those experiments here though. So question 5 is we have a bisubstrate reactant and it follows ping pong. So we have product P and it's labeled. So we have a atom in there that's radioactive. The question is, if I add P in our enzyme to our mixture, would we find any A that has been labeled? And yes, because in ping pong, you only need one substrate to bind, and enzymes can move backwards. So if we have P that's labeled, what can happen is that this P will bind to the enzyme and work backwards to remake A. So it is possible, if you just have enzyme in P, to go backwards and create radio-labeled A. While question 6 is the same thing, but we are no longer ping-pong versus sequential. So if I only add radio-labeled P in our enzyme, can we find radio-labeled A? And we can't. Because if I want to go backwards from P, the only way that works is if I have Q as well. So I cannot go backwards unless I have both products available. So I cannot make A unless I have Q if it's sequential. So that's the big difference again. Ping pong, substrate binds, product comes off. Second substrate binds, second product comes off. Sequential, both substrates bind, both products come off. And that's it for this video. I will see you in the next video.